For our next type of multivariable graph, we're going to talk about cylinders. Now, I know you think you know what a cylinder is. When you envision that cylinder, you're thinking of like a tin can. So it's a circle on top and a circle on bottom, and then, the can in between. That's a type of cylinder, but it's not the only type of cylinder. Mathematically, a cylinder is actually any three-dimensional graph of an equation that contains only two of the possible three-dimensional variables. So an equation of a cylinder contains two variables. The two-dimensional graph is a cross-section of that cylinder, and the three-dimensional graph of the equation looks like the cross-section, but it's pulled parallel to the axis of the missing variable. This is the cylinder. Right? This is what a cylinder is. So it's not what you think of from geometry class and from, looking at tin cans in the store. Okay, so let's look at this first example, and this will help hopefully clarify it. Of course, it can look a little bit like the tin can, and this one's going to. So this we all know from algebra. That's a circle. It has a center at 0, 0, and it has a radius equal to 3. All right, so if I looked at a cross section, right, because it says a two-dimensional graph of this is a cross section. So let me draw a cross section, which is a 2D graph. All right, so I have my x-axis and my y-axis. 1, 2, 3, 1, 2, 3. This is not the best scale I've ever drawn in my life, because I am not a good drawer, and I apologize. That's a circle, right? It's a circle. Radius 3, origin at 0, 0 for the center. All right? But that's a cross section. Now look, there's no z in this equation. No z given, right? So note z is missing from the equation. So z can be anything, right? Z is the entire real number set. It's free to be anything it wants. All right, so I'm going to draw this cross section that I'd had out here on the plane. 1, 2, 3, not the z down there, but in here. 1, 2, 3, 1, 2, 3. It'll look a little weird, of course, because I'm on the XY plane, so it'll look a little strange. It'll look more like an oval, but it's technically a circle if we looked at it from straight down the z-axis. That is that cross section. That is that circle drawn over here. So it's hitting at 3 and negative 3 and 3 and all that good stuff. And the trick is that z is allowed to be anything. So the up and down part, let's see if I can draw this straight, can be whatever it wants to be. So it's pulled, it's stretched, technically infinitely, in the z direction, right? And so we have right, and it keeps going and going and going and going, right? Z is anything, right? It's pulled parallel to that mixing axis. So it's pulled in the z direction, I guess I should say, or parallel to, I guess I should just say parallel to the z-axis. Fun, huh? All right. Before I go any further, let me pull up Maple and let you see this and what this looks like. There it is. So x squared plus y squared equals 9. I let x and y both go to technically 5, but it didn't even draw them all because the graph stops at 3. So it stopped it at 3. And then look right there. Look, if you look down it, it's a circle, but then it stretches. And this one stops at the negative 5 and 5 because that's just where I stopped my z. I could go to 10 and negative 10, no problem. Like that. There. And I boosted my transparency there just so you could see it a little bit. Maybe I'll make it 0.2. Let's see how that goes. There you go. Just so you can see in the cylinder, there's the axes right there. I did that with transparency over here. And you can see there's a cylinder and it's stretched in that z direction. And actually, because of the way it graphed this, if I play with it, there you go. You can kind of see, oh, the cross sections are circles, right? You can kind of see it because of how they graph it in Maple. But of course, if you're looking down the barrel, there's the circle that we drew. That's the cross-sectional circle. Transparency, by the way, is, I believe, a decimal or a percent between 0 and 1. So if I make it 0, it's completely opaque. And if I make it 1, that's completely transparent. At least that's how I remember it. All right, so let's do the next one, which is z equals y squared. Okay, well, let's think cross section again. I'm going to stick with my ugly colors, but because I like the high contrast. Sorry about that. All right, so z equals y squared. Well, the cross section would not be on the xy plane, it would be on the yz plane. So it'd have, because y and z are the only variables here. So this would be the y-axis. I'm thinking about how I'm going to have to draw this over here. And this is the z-axis right here. And so if I go 2, 1, 2, 3, 4, 1, 2, it's going to look like that, right? It's a parabola, right? And so I want to draw that parabola over here. 1, 2, 1, 2, 3, 4. It's going to go from that point down to that point. 2, 1, 2, 3, 4. And I'm kind of out at that point, even though technically the curve continues on, right? It keeps going like this. But here's the thing. It's stretched in the x direction, right? So I want to kind of mimic that curve over here and mimic that curve over here. And then I'm going to connect them. It's sort of like a trough, right? Oop, I got to connect those tips down there. I didn't do the best job of that. There you go. See? So it's stretched in the x direction. So it's a parabola, if you will, because that's a parabola. And it's stretched in the x direction. And of course, I can show you this in Maple. I'm going to make the cylinder go away. And there we have it. So it's a parabola. See, there's a parabola, but it's stretched along the x-axis. Like that, like a big fold of paper. All right, now let's look at the last one, which is x equals e to the z. All right, well, we know what e to the x looks like, right? So e to the z will look like the same thing. It's just, it will look like it on the, let's see, x, z plane. So we got to think of this kind of in reverse. It's not going to be e to the x. That looks like this. But it's e to the z. So the z piece is over here. It's going to look like a logarithm because it's an inverse function, right? All right, and then it's going to stretch it in the, well, here, let me write. Cross section is, it's a logarithmic function, right? It's technically an inverse exponential function. So logarithmic. And it, of course, hits at 1, right? When z is equal to 0, x is equal to 1, right? If z is equal to 1, x is equal to 2 point and some change. So here's 1, and here's e, which is 2.7 and some change. Stuff like that, okay? All right, so it's logarithmic. It's the inverse, right? It's inverse exponential, if you want to think of it that way, because that's what logarithms are. And it's stretched in the y direction. So we're going to stretch it left to right. But first we have to kind of draw this piece. And this is going to be a little tricky to draw here. We know that when x is 1, z is 0. So it's going to hit that point right there. And then let's think about down here. Down here, x is even smaller. So that's over here. I'm going to actually shade this in 2 colors just to help us. So that's going to be kind of this piece. It's kind of sticking down like that. And then it's going to be going up and growing out, right, from the YZ plane. So it's going to come out and go this way. But I'm in this plane. I'm in this XZ plane as I draw. So let me make it pink just so you guys can see it. So it's going to kind of go like this and be shooting out. I don't want to make it seem like it's following that y-axis because it's not. It's going up, 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 like that. But it's still in that, it's constantly in that xz plane. It is this piece that I'm drawing. And then you just stretch it in the y direction. So you make a mimic of that curve over here and a mimic of that curve over here. You're stretching it left to right because that's the way the y-axis works. And it makes it fold like this. And it's a little hard to see, but you're doing this, right? This one's particularly tough to see. So why not look at it in Maple? Maple will do a better job than we would. So let's look at it. It looks like that, right? So what we're trying to do is draw that curve kind of coming up and then draw companions for it on the left and the right and make it connect. And of course, if transparency is your thing, if you want to see through the axis a little bit better, you can add in a transparency equals 0.2 to it and then hit enter. And there you go. You can see, right? There's the axes a little bit better. And that's kind of what we're trying to draw. And now I just want to remind you, all of these graphs. So the first one, which actually looks like a tin can, but technically goes on infinitely into the z direction and both positive and negative. And then these other two, this one's like a parabola sheet of paper, and this one's like just a folded sheet of paper. All three of them are cylinders as far as Calculus 3 is concerned, right? The definition of cylinder is no longer a tin can, right? It can be anything as long as it's stretched and pulled in this direction, right? So that's what you're looking for. You're looking for pulling in this direction. And the reason that happens is you have a missing variable, right? So that missing variable is very important. That's what a cylinder is for us. A cylinder has two variables. A 2D graph is a cross section. The 3D graph is pulled in the direction of the missing variable. This is what a cylinder is as far as we are concerned.